Okay, so in this video, I wanted to talk about Michelson Morley experiment, but in particular, just at the high school level, HSC level, because I've seen a lot of kind of misconceptions surrounding it. So, in terms of what it's originally for in the context, Michelson Morley, along with a bunch of other physicists at the time, believed that there was this thing called the ether, and that is just some undetectable omnipresent kind of quantity that was just everywhere, and the speed of light was supposedly meant to be constant relative to the ether. And so whenever you had objects moving with respect to that ether, that's when they expected to see different velocities of the speed of light, which of course now you know is not true, because Einstein came up with those postulates later that stated regardless of what frame of reference you're looking at, the speed of light is constant. But when you think about this experiment, you need to think about it in the context of someone who doesn't know that the speed of light is constant in all frames of reference. Okay, so we're going to do a couple of manipulations that might seem strange if you know about Einstein's postulates, but this is what Michelson Morley was kind of trying to show. So if you look at this current diagram here, basically what it shows you is a half silvered mirror. And basically what that does is it splits any sort of light beams. And so there's this light source here, and that light source beam is being split into kind of two separate beams, and they're reflected off these mirrors here, which are an equal distance away from the silvered this beam splitter in the middle. And then they're recombined. And when they're recombined, you know that when you have two sources of waves, provided that certain conditions are met, then they will undergo interference and create a maxima and a minima pattern. And that's what you would expect at the detector. So at the detector, you would have some maxima, and then some darkness, and then another maxima with slightly less intensity, so on and so forth, right? So you'd have these maximas, something like this. And what Michelson Morley did was they kind of indicated where that interference pattern was position-wise. So they put a red line there and said, okay, this is where the interference pattern is when this whole apparatus is stable, supposedly relative to the ether, right? So then what they were trying to investigate is what would happen when this apparatus started moving. And there was this kind of process of logic where they said, okay, if this whole apparatus moves relative to that ether I was talking about earlier, then what they expect is that this interference pattern, should shift. Okay, so how they detected that shift is that this red line should shift towards the right. Obviously, I'm exaggerating here, but what they sort of indicate is that whole interference pattern shifts in a certain direction relative to the red line indicator that they put in earlier. That's what they expect, right? And we're going to show you how they came up with that conclusion in just a second. But in the end, what they discovered was that there was no shift. This red line stayed in the center, regardless of where they put this interferometer, at what time that they used this interferometer in the year, regardless of what the Earth's velocity was, etc., whether it was at the equator, whether it was at the poles, didn't matter where it was, right? There was no shift, which indicated that the speed of light was constant in all frames of reference, as opposed to just in the ether. Okay, so let's think about how Michelson and Morley came up with this original kind of idea that it should shift. So what I've done is I've drawn a couple of diagrams that show kind of different frames, I guess, or different points in time as this thing is moving. So what we have to first establish is that this whole apparatus is moving at some velocity v. Okay, now usually the v is because of the interferometer itself being on Earth, and Earth has some relative velocity to the so-called ether, and that's where this v comes from, okay? So this whole interferometer is moving at v, and I've got these solid lines which show where the apparatus is at the moment, and later on in the diagrams you'll see I draw dotted lines to show where the apparatus was and where it is now, represented by the solid lines. So initially, to begin the process, you have this first initial beam of light, and afterwards, this whole apparatus has moved a little, and when it has moved a little, the beam of light, as viewed from an external observer, has traveled up to one of the mirrors, right? So originally when it's stationary, it kind of just looks straight up, but when we're looking at it from an external observer's point of view, it will look like this, diagonal, right? And furthermore, you'll see that originally the light would have only had to travel up to this point here to reach one of the mirrors, but because the mirrors also shift during the time that the light takes to move, and so the mirror has now shifted up to this point. And so, in essence, the light has to actually travel further than it would have before to reach that second mirror. Okay, so this is a very kind of important point here. So, if we can quantify the distance that these mirrors travel in this given time, so let's say that because this whole apparatus moves at a velocity v, and let's say that a time t has passed, therefore the distance traveled by this mirror is equal to vt, right? Fair to say, vt equals the distance, right? And we also know that in this same amount of time, the speed of or the light has traveled from this point here to this point here, right? So let's call that distance ct, where c is the speed of light, right? Ct. And then, so what you can see here is you have an application of Pythagoras, right? Where we have, and let's call this t1, just to indicate that this is the first path here, t1, and this is, so if we go vt1 all squared plus L squared is equal to CT1 all squared. And I'm not going to go into the arithmetic, but if you simplify this, you should get T1 is equal to L on square root C squared minus V squared. So then afterwards, we'll leave it there for now. And with T2, which is referring to this bottom kind of beam of light traveling here, remember how I said that this mirror here has moved a certain distance during the time it takes for the light to travel, right? So it's moved some extra distance. And so when this whole light is traveling, if we ignore the fact that the speed of light is constant in all frames of references and say that it acts like Galilean relativity, like some normal sort of, velocity difference between frames of references, then in that case, we could say that this speed of light relative to the mirror is actually traveling at c minus v, right? It's kind of like if you're chasing someone with some velocity, v1, and they're moving away from you at some velocity v2, then the relative velocity of you to that person you're chasing is going to be v1 minus v2, right? So in the same sense, this speed of light, relative to this mirror here is c minus v. We know that's not true now because of Einstein's postulate, but at the time they believed that was the case, right? So c minus v. So in that case, if we're trying to figure out the time taken for this light to get to that mirror, then hopefully you can see that that would be T2 is equal to the distance, which is L on c minus v, right? So you're traveling some distance L, which is, that shouldn't be a small case, should be a large case. So you're traveling some distance L between the half-silvered mirror and the blue mirror here, and you have some relative velocity c minus v, right? So T2 equals to L on c minus v, and you've taken into account the fact that this mirror is shifting along at velocity v, okay? So you got T1 and T2 here, and then we move on to the next frame. So now this whole setup has shifted even further, right? So now the solid components, which represent the position of the interferometer at the moment, has shifted even further. And so what we expect is that by symmetry, the distance, well, not the distance, but the time that we calculated for this here should be the same as the time we calculated for this here, right, by symmetry. And so in that case, the total time taken to go from, here up to here and then down back to here, that total time taken should be equal to this times by 2, right, T1 times by 2. So T1 or 2T1, and we'll give that a capital T1, should be equal to 2L on square root c squared minus v squared, c squared minus v squared. And then Down here, it's a little bit more complicated because if we look at how this light is kind of traveling down here, so at the moment earlier where it's been reflected off this point here, it starts traveling backwards, right? But this time, as it's traveling backwards, the beam splitter that it's traveling towards is also traveling towards the light itself, right? You can see this beam splitter has some velocity in this direction, right? And the light is trying to travel back to the beam splitter. So in essence, it actually has some relative velocity that's higher than the speed of light, right? So in that case, the time taken to travel back to that beam splitter is actually L on C plus V, right? So you can imagine this as if I am, running towards a friend that I haven't seen in a long time, and they're also running towards me, then we're going to have some relative velocity, which is the addition of our two velocities, right? We're going to reach each other sooner than if it was only me running towards my friend, because, my other friend might not be as happy to see me, right? So you have two velocities and they're added together to find the relative velocity if they're both moving towards one another, right? So you can see this T2 is actually different from this T1, because in one case the light is chasing the apparatus, if you will, and the other time the light is actually moving towards the apparatus, and the apparatus is also moving towards the light, right? So that's T2. So if we add our two T2s together, our capital T2 is going to be, and maybe I should give this a T2 dash to indicate that it's different, should be equal to T2 plus T2 dash, which is equal to L on C minus V plus L on C plus V, okay? And if I put this all together, that should give me 2L on C, 1 minus V squared on C squared, okay? So I'll leave that up to you to kind of deduce why that's the case. So T1 up here is 2L on, so I've actually 2L on, so 2L on square root C squared minus V squared. And we might want to make this a little bit nicer. This is actually, should be 2L on C minus 1 minus V on squared on C squared. And up here, this one should be, so this is the correct one, but perhaps we should rearrange it so that it's a bit nicer and comparable to this one down here. So this one should be C square root 1 minus V squared on C squared. So 2L C square root 1 minus V squared on C squared. And then down here, 2L, but without the square root. That's the only difference, right? That's the only difference. Okay, so we've gotten two kind of components here. One's this one here, which is T1, and this one's here, T2. So these two expressions represent the time difference, or not really the time difference, but the individual times taken for the first beam of light to travel back to the beam splitter, and the time taken for the second beam of light to travel back to the time splitter. Yeah, so this one's T1 is equivalent to the time taken to travel this path here, and then time 2 is the time taken to travel this path here, right? And this is given that the whole apparatus is moving at some velocity v relative to the so-called ether. So then you have T1 and T2. Now, if you look at these two times, you should notice that obviously if we substitute any sort of value into here, we actually get numbers that... So if you compare these two times, what you should see is that T2 is greater than T1, right? And you can substitute any sort of v value into here, for example 0.8c, to kind of convince yourself that that's true. But essentially the time taken in the axes in which there's actually relative velocity should be longer than the time taken in the axes where there's no relative velocity. Okay, so T2 is greater than T1. So in the end, what Michelson and Morley predicted is that there would be this time difference between the two beams that are split off. And because of this time difference, therefore these beams of light would return to the half-silvered mirror out of phase. And because they return to the mirror out of phase, and therefore the interference pattern should be shifted compared to when the whole setup is stationary, and that is why he predicted that this interference pattern should shift relative to some reference point that I've represented here as a red line. But in the end, hopefully you realize that in fact none of this was observed. This time here was not actually different. This interference pattern was not shifted relative to the red reference point. In fact, what this proved, what is called a null result, because nothing that he predicted actually happened, a null result proved that the speed of light was in fact constant relative to all frames of reference, as opposed to what he assumed, which was that the speed of light changed depending on whether you were moving or stationary, which is what we assumed when we did all of these derivations here, when we did c minus v, and also when we did c plus v down here. Okay, so hopefully that clears up some questions about what Michelson Morley's experiment is for, and some of the things he expected and the results he ended up getting. If you have any questions about it, you can always contact me